Here we have a problem that involves Cartesian vectors. So we're given three forces that act on the origin. F1 is given to us as a magnitude, and then we see the three angles, and then F2 and F3 are given to us as Cartesian coordinates, as Cartesian vectors. So the first step that we're asked to do in A is to find the Cartesian vector of the resultant force Fr. Now to do that, we'll first have to find the Cartesian vector for F1 so we can add them together easily. So let's start that. Right? We know that F1 is equal to the magnitude F1 times now the cosine of alpha 1 times I plus the cosine of beta 1 times j plus the cosine of gamma 1 times k. Right, that's by definition what we get. If we write that out, then we get 1.75 kilonewton times the cosine of 36 degrees in the I direction plus cosine of 114.3 degrees in the j direction plus 50, not 53 by itself, but cosine of 53.7 degrees in the k direction. All right, so we can figure out what those cosines are and multiply them by 1.75 kilonewton, and then we get the following vector: 1.42 in the I direction minus 0.72 in the j direction and plus 104 in the k direction. And because this is a vector, because it's a force, it's all in kilonewton. So that would be our F1. Now if we want to get Fr, our resultant, right, that's just going to be F1 plus F2 plus F3, right? The idea is they're all Cartesian vectors, so they'll be easy to add together. So what do we get there then? We get Fr is equal to F1 we just created there, so it'd be 1.42I minus 0.72J plus 104K kilonewton, and then F2 is there, 0.3 minus 0.65, so that'll be plus 0.3I minus 0.65J. I'm not going to add all the extra zeros there. And then plus 0.3K. That was also kilonewtons, I'm assuming, not newtons, yeah. Kilonewton. Plus F3. Can't quite get it on there. Minus 125 plus 0.9, so minus 1.25I plus 0.95J minus 3K kilonewton. Now to make this very clear here, let's do an extra step, right? So we're equal to, so let's write all the i's together, all the j's, and all the k's together. So let's do a square bracket for the unit, and then we'd have from the first one 1.42, from the second one 0.3, from the third one 1.25. This is all I. And then from J, we get minus 0.72 from the first, minus 0.65 from the second, plus 0.95 from the third. That's all J. Plus all the K, so that'd be 1.04 plus 0.3 minus 3 K. And that should be, so I say square bracket from the outside, and all that is in kilonewton. Well, let's see, does that all make sense? All looks good to me. 1.42, 0.3 minus 125, minus 0.65, right, plus 0, 1403, and minus 3. So all that looks good. So if we just write those together, right, then I can say we get 0.466i minus 0.420j minus 1.66k kilonewton. And that would be our answer. Right, this would be our resultant vector. So that was point A. We probably should point A in front of here. A. All right, so B is then what is the magnitude? Well, we have a Cartesian vector. That's easy to do. So B, we're asking for the magnitude of FR. Well, you can also just use it as FR without the vector sign on top. And that, of course, is just FRX squared plus FRY squared plus FRZ squared. That means in our case, that would be square root of 0.466 kilonewton squared plus minus 0.420 kilonewton squared. It doesn't really matter to write the negative sign there or not because we're squaring it, but let's make it clear. Minus 1.66 kilonewton squared, and all of that square root. And I get for that 1.78 kilonewton. So that would be the magnitude. That was B. And then C, give the direction angles, alpha, beta, and gamma for FR. All right, let's see. So that would be alpha R, right? That's the inverse cosine of FRX over FR. All right, very good. So that means cosine minus 1 of FRX was 0. I'm missing a 6 here. 0.466 kilonewton divided by 1.78 kilonewton. What just calculated. And so that gives me 74.8 degrees, right, from the positive x-axis. Then beta R is cosine minus 1 of FRY over FR. So that'd be cosine minus 1. Where do we have? That'd be minus 0.420 kilonewton, 1.78 kilonewton. So of course for these 1.78 and even for the numbers up here, probably want to use whatever's left in our calculator, right? So we reduce the rounding errors. If we plug all that in here, it's important that we have the negative sign, right? Because we're not squaring or anything like that. So we get 104 degrees from the positive y-axis. And then the gamma, which is our last one, gamma r, is then cosine minus 1 of frz over fr is equal to cosine minus 1 of fr minus 1.66 kilonewton over 1.78 kilonewton, and that gives me 159 degrees. All right, with that we have our three directional angles. That was C, then D. I'm going to give all the unit vectors. All right, let's see. D. Unit vectors. F1. So F1, we can directly give the unit vector because we have the angles. So we can say that our UF1 is going to be just cosine alpha 1 I plus cosine beta 1 J plus cosine gamma 1 K. All right, that's pretty straightforward. So that means we get cosine of 36 degrees times I plus cosine of 114.3 degrees times J plus cosine of 53.7 degrees in the K direction. And if we plug those numbers in, I get 0.81 I minus 0.41 J plus 0.59 K. That's our first unit vector. Now for the other unit vectors, we're not given the directional angle, so we'll have to find out what the magnitude is and then divide the Cartesian vector by the magnitude. So we'll start by finding the magnitude of F2. Right, that'd be square root of all the squares, right? So that'd be 0.3 kilonewton squared plus minus 0.65 kilonewton squared plus 0.3 kilonewton squared, and that gives me 0.776 kilonewton. That's the magnitude. So if I want to get my unit vector, then I'd have UF2 would just be F2 divided by the magnitude of F2. So that would be, where do we have it? 0.3 I minus 0.65 J plus 0.3 K, kilonewton, divided by what we just calculated, 0.776 kilonewton. So we can just divide those out, right? That's not going to give us anything directly, so we'll just do it by decimal points. So we will get 0.39 I. We don't need the bracket there because it's our unit vector. We don't have a unit. 0.39 I minus 0.84 J plus 0.39k. And remember, if we wanted to check on this, right, we could just square each of those up and add them together, and that should give us 1 in the end. All right, so then off to our last one. So we have to do the same thing. We'll have to find the magnitude first. So F3 is equal to the square root of minus 1.25 kilonewtons squared plus 0.95 kilonewtons squared plus minus 3 kilonewtons squared. And that gives me 3.386 kilonewton. So we can do the same thing again here. Now for UF3, right, that would be the vector F3 divided by its own magnitude. So that would be minus 125I plus 0.95J minus 3K, all that kilonewton, divided by, which I just calculated, so 3.386 kilonewton. So again, of course, the kilonewtons cancel out, and we get minus 0.37I plus 0.28J minus 8. Let's make that 8 a little more readable. And then minus 0.89k. Oops. That's not a vector. There we go. So that would be our unit vector for our force F3. And then for the main one, for the resultant one, we can again use the angles that we just calculated. So U would be FR is then equal cosine alpha R I plus cosine beta R J plus cosine gamma R K. So that is cosine of 74.8 degrees I plus cosine 104 degrees J plus cosine of 159 degrees K, and that gives us 0.26 I minus 0.24 J minus 0.93 K. That would be the unit vector for our resultant force. So with that, we have all the unit vectors, and with that, we have everything solved, right? So this was a problem about Cartesian vectors, where we had two Cartesian vectors plus a vector with magnitude and angles, and we found what the resultant of those three is, and we found the magnitude of the resultant, the angles, and then unit vectors for all of the different vectors that were involved.